In the last class, we discussed about what would be the resistance for heat flow through a planar wall or a combination of several plane walls. And there we saw that the temperature difference between two ends of the wall can be viewed as the potential difference which causes the heat to flow from high temperature to low temperature. And the resistance, the heat flow can be expressed in the form which is similar to that of Ohm's law, where the potential difference is to be replaced by the temperature difference and the current is to be replaced by the heat flow. And whatever we have in the denominator of Q equals delta T by R, this R is equivalent to thermal resistance. And the thermal resistance we have evaluated for a plane wall, and also if we have several such walls sandwiched one after the other, then the overall temperature difference between the outer edge of wall 1 and the outer edge of wall n, this temperature difference is the overall temperature difference, overall potential gradient, and the denominator is going to be a sum of all the individual resistances of each of these walls. So, in essence, the heat flow through a composite wall where cross-sectional areas remain the same at steady state can be expressed as heat flow equal to the overall temperature difference by the sum of all resistances, and therefore, all these resistances it has been shown that they are in series. So, based on that we clearly understood that what is the resistance of the plane wall. It is going to depend on the geometry, that means what is the cross sectional area, what is the thickness, and it also going to depend on the thermophysical property, which is the thermal conductivity of the specific wall that we are considering. So, the resistance is simply going to be L, where L is the thickness, divided by K times A, K the thermal conductivity of the material, and A is the flow, the area which is perpendicular to the direction of heat flow. We have also seen that for composite walls of different type, in which you have wall number 1 whose area is A, then another wall of different thermal conductivity whose area is, let us say, A by 2, and another wall number 3 whose area is also A by 2, but it is of another material. So, when such walls, composite walls of unequal cross sectional area are put together, then there are two ways by which you can represent the heat flow. One is you can assume that there is going to be a series, there is going to be the top 3 are going to be in series, whereas the top and the bottom series are going to be in parallel. So, we discussed about that as well. One of the characteristic features of heat flow through plane wall is that the heat flow is constant. Not only heat flow at steady state the heat flow is constant, and not only the heat flow, the heat flux is also constant, since the cross sectional area for which is perpendicular to the direction of heat flow does not change. So, as in planar systems, the cross sectional area does not change with x, with the direction of heat flow. Therefore, both the heat rate and the heat flux are going to be constant. However, I have mentioned in the previous class that for radial systems and for spherical systems, in which as you move in the direction of r, the cross sectional area keeps on changing, and therefore, even though the conservation equation demands that heat rate has to be a constant, the flux may not be a constant, and therefore, we are going to have a different expression for the resistance to heat flow for the case of radial systems and for spherical systems. So, that is what we are going to analyze in today's class. So, it is going to be temperature distribution in radial temperature distribution at steady state in radial flow of heat, and the mode of heat transfer is conduction but you can always have convection at the outer or the inner edges of a radial of a wall, and therefore in that case it's going to become a convection conduction problem. But for the time being, let's start first with conduction only case in a radial system. So the figure that you see over here is that of a hollow cylinder whose inner radius is equal to r I and the outer radius is r naught, and the temperature over here at the inside is maintained at T I, whereas the temperature at the outside is maintained at T O. So this is the situation. The length of the cylinder, hollow cylinder, is L, and we are trying to find out what is the flow of heat through this area to outside. So if we assume that T I is greater than T O, if T I is greater than T O, then this is the radial direction in which heat will flow through the solid material of the cylinder, and we are trying to find out what is going to be the resistance for heat flow. For this case, for steady state condition, for steady state with no heat generation and the case where T, as you can see, is going to be a function of r only, it is definitely not a function of theta and it is not a function of z. So, T is a function of r only. Therefore, the heat diffusion equation for radial systems reduces to only this much, because we do not have to consider the variation of temperature with r or theta. So, T is not a function of either z or theta. So, therefore, all the terms containing gradient of T with respect to z or with respect to theta can be cancelled. It is a steady state one. So, this T is not a function. So, T is not a function of time and there is no heat generation. So, therefore, if you look at the heat diffusion equation, this is the form it is going to take. Okay. And one can integrate this equation, and what you get is T r equals C 1 ln r plus C 2. In the two boundary conditions, this is the governing equation. So, this is your governing equation, and in order to solve the governing equation, you need two boundary conditions, which are the two known temperatures in this case. So, T at r I is equal to T I, and the second is T at r naught is equal to T naught. So, when you put these two boundary conditions to evaluate C 1 and C 2, the final expression what you are going to get is T I minus T naught by ln r I by r 0 plus times ln r by r 2 plus T 0. So, here what is I think we should appreciate is that the temperature distribution, unlike the case of planar system, is not a linear function of position, but it is going to be a logarithmic function of the radial location of the plate. So, so that is very important to note that it is no longer going to be a linear distribution, it is going to be a logarithmic distribution. And as we move in the direction towards the outer radius, the area of heat flow, the area available for heat flow continuously increases. So, since it increases, the temperature is not going to be linear, and temperature here you can see it is going to be linear function of position. Now, what is remaining is since we are trying to correlate cause and effect, the cause being the temperature difference and the effect being the heat flow, and we are trying to find a relation or express our results in the form of something similar to Ohm's law between cause and effect. So, if you do that to this equation, the automatically the resistance to conductive heat transfer in radial systems will come out. So, that would be our next exercise to see what form the resistance would take in a radial system. So, if you look at this equation once again, then I can write this from this equation. I can write dt dr is equal to T I minus T naught by ln R I by R naught times 1 by R. Okay. So, with this, using Fourier's law, the q is simply going to be, q in the radial direction is simply going to be minus k 2 pi L, L being the length of the cylinder, times T I minus T naught by ln R I by R naught, or it is 2 pi k L T I minus T naught by ln R 0 by R I. So, if I take this to the next logical step, and here you see this is the effect and this is the cause. So, if I bring twice pi k L in the denominator, what you have is something similar to Ohm's law, where the cause is the potential difference, is the thermal potential difference, which is expressed as temperature difference, and the effect is the radial flow of heat. And what I have in the denominator, ln R naught by R I by twice pi k L, that simply is the resistance to heat transfer for radial systems. So, I am going to write it in the next page as temperature difference So, what you have here in the denominator is your resistance, the thermal resistance, which obviously is this. So, this is an important result which gives us what would be the resistance to heat transfer in such case. And let us assume that you have a composite situation in which you have a number of walls like this. This is R2, similarly you have R3 and R4, with each one having thermal conductivity of K1, K2 and K3, and you also have convection inside as well as convection outside, with the inside condition given as the temperature of the fluid in here is T infinity 1, which is creating a convection coefficient of H1 at the inner surface of the composite wall. On the other side, you have T infinity 2 as the temperature of the fluid, which is made to flow on the outside, which is also producing a convective heat transfer coefficient of H2. This is quite common in many of the practical situations. For example, in heat exchangers, which we would see, where the hot fluid, let us assume that it is flowing through a tube, and somehow it is going to come in contact, in thermal contact with a cold fluid, with which it will exchange heat, and therefore, the cold heat is going to be heated, going to absorb, going to gain energy out of this hot fluid. And let us say a hot fluid is flowing from point A to point B, from where it is produced to where, let us say, it is going to a reactor. So, in the transit, you want to maintain the heat loss to a minimum, you want to keep the heat loss to a minimum. So, how do you do that? You put insulation on top of the pipe, on top of the tube. So, this insulation, the pipe and the insulation, there may be 2 or 3 different types of insulation. One is an insulation which is thermally, which is going to protect heat loss, which is going to minimize heat loss, and in order to protect the insulation you may have another outer cover. So as the heat travels from the inside to the outside, it's going to experience different materials as it travels, and it's going to also see materials of different thermal conductivity, and as it travels it will see that the heat transfer area will keep on changing. So under such circumstances, what you are going to get is the picture that I have drawn, where you have a composite wall where in the inside you have some convection coefficient, and at the outside you have a different convection coefficient, which is probably provided by the ambient air which flows over the lagged pipe. So what would happen to such a case is depicted over here, and I am simply going to write what is the form of the final equation going to be. So the radial flow of heat is going to be due to the temperature difference inside minus temperature difference outside. So what you have is T infinity 1 minus T infinity 2. That's the reason why the heat is flowing, divided by the sum of all resistances. So what is the resistance for the first one? As we have discussed before over here, so it's simply going to be ln R2 by R1 divided by twice pi k of material, let's say this is A, B and C, Ka times L, and then the second one would take over. So this is going to be ln R3 by R2 by twice pi Kb times L plus ln R4 by R3 by twice pi Kc into L. So these are the 3 conduction resistances through the material A, B and C. I also have a convection which is taking place over here. So what is the convection? The convective heat transfer QR between this point and this point is simply going to be T infinity 1 minus T, this is T1 divided by 1 by twice pi R1, 1 by twice pi R1 times length, okay, times h. This comes from Newton's law of cooling, which simply says that QR is HA times delta T, and in this case H is H1 times area is twice pi R1 L, because this is the area which is exposed to convection environment, times T infinity 1 minus T1. So from here I have written it in the form of temperature difference by some sort of a resistance. So this is the expression for convective heat transfer resistance in the case of radial systems. So this must be added to this overall resistance twice pi R1 L H1 plus, and over here it's going to be 1 by twice pi the last R4 L times H2. So I think it is clear to you now is that what happens in this case where you have multiple walls, radial walls, one after the other of different thermal conductivities. The inside is exposed to a convection environment, the outside is also exposed to another convection environment with 2 different temperatures and 2 different heat transfer coefficients. So the heat flow, which has to remain constant in order to maintain equation of conservation of energy, is the overall temperature difference, which is T infinity 1 minus T infinity 2 by the sum of all resistances. And what I mean by the sum of all resistances is the convection resistance on the inside, all the possible conduction resistances that the heat flow is going to face. So, if there are 3 walls, there is going to be 3 different conduction resistances, and when it reaches the outer edge of the outer wall, it experiences a convection once again. And from Newton's law of cooling, we have seen how we can express the heat flow as temperature difference divided by a resistance, and the convective heat transfer resistance is expressed as 1 by HA, and the area simply is going to be twice pi r times length. That is the cross section, that is the inner area of the inner cylinder. So, this way you can quite easily write what would be the form of the equation for radial flow in systems, and as I mentioned, they are very common in many industrial situations. Now, what I would do next is something very interesting. Is normally what we feel is that if I am feeling cold, I just wear a sweater, which is nothing but an insulation, and this reduces the loss of heat from my body to the ambient, and I do not feel cold anymore. So, in the purpose of the sweater or the jacket is to ensure that the heat flow from my body to the ambient gets lowered. That is what insulations do. They reduce the flow of heat from the hot object to the cold object. But is it ever possible that by adding an insulation you are making more or higher flow of heat from the hot object to the cold object? So, this is counterintuitive, but it may happen, and I am going to show how, under what conditions, by adding insulations you simply increase the rate of flow of heat through that insulation. So, that is a very interesting concept. It is known as the critical thickness of insulation. So, if your thickness of insulation is below a certain limit, then by adding insulation you increase heat flow. If it is above the critical insulation thickness, by adding insulation, what you get is what we commonly expect, that the heat flow rate reduces. But the interesting part is that region in which your size is below that of critical thickness of insulation. So, by adding insulation, you are increasing the loss of heat. So, you would first mathematically see what needs to happen for you to decide what is this critical thickness of insulation, and then we will talk about some of the practical uses, practical situations in which you may expect to encounter critical thickness of insulation, and it has certain advantages as well, and what is the scientific reason for such thing to happen. So, let us look at the derivation once again. So, next I go to critical thickness of insulation. Let us say I have a cylinder and a solid cylinder and an insulation. So, this is R I, and let us assume that the temperature here is maintained at T I, temperature at the junction between the solid rod and the insulation. So, this is your insulation, and the insulation radius is R naught, and on the outside it is exposed to a convection environment with temperature and heat transfer coefficient as H and T infinity. So, it is a solid rod of radius R I, the junction temperature is at T I, the insulation radius is R naught, and it is exposed to H and T infinity. So, as before, from here I can write that the heat flow is simply going to be T I minus T infinity divided by the resistance of heat flow through this, which is ln R naught by R I, exactly following what we have done before, divided by twice pi k L, where L is the length of the cylinder, plus I have the convective resistance, which is 1 by h twice pi r naught L. So, there is nothing new. I have simply used this for a system for this case. So, if this is Q, then I am going to see is it possible to mathematically get at which point my heat flow is going to be maximum. So, if I can do that, then I will probably get an idea of what is the concept of critical thickness of insulation. So, starting with this Q, which is, I will write it again, T I minus T infinity by ln r naught by r I twice pi k L plus 1 by h 2 pi r naught L. I am going to differentiate this and set this to be equal to 0. So, I am trying to find out, is there a radius r 0 where r 0 is the insulation thickness which would maximize the flow of heat, which is denoted by Q. So, if I do this, then what I am going to get is twice pi L T I minus T infinity 1 by k r 0 minus 1 by h r 0 square divided by, this is straightforward maths, there is nothing over it. So, for this to be 0, 1 by k r 0 must be equal to 1 by h r 0 square, and what you get, r 0 is equal to k by h. This r 0, the critical the thickness of the insulation which would maximize heat flow, is known as the critical insulation thickness. So, this critical insulation thickness, therefore, it tells you that if you have a solid cylinder and you are putting insulations around it. So, this is your first level of insulation, this is your and then at the next instant you increase the thickness of insulation some more, and you are going to increase the thickness even more. As long as your radius of this, as you are adding, so if you are if so, let us say this is r 0, which is equal to k by h. As long as you are below this value, you are less than k 0 by h, your Q will increase. So, if r 0 is less than k by h, add insulation, Q will increase. If r 0 is greater than k by h, add insulation and Q will decrease. So, this is the concept of critical insulation thickness. So, there exists a thickness when, if you add insulation, the heat flow will increase. Go beyond that and you add insulation, and the expected thing will take place, that is, the heat flow will decrease. Now, why it should happen? This can only happen when the thickness is very small. So, when the thickness is very small, by adding another layer of insulation, you are increasing the resistance for flow of heat through that added layer of insulation. That means, you are increasing the conduction resistance by making the layer thicker. However, with putting the layer of insulation on the outside, you are making more area available for conduction, because the area available for conduction is simply twice pi r multiplied by length. Length is a constant. So, as r increases, your area available for convection increases. So, there is with increase in R, the conduction resistance will increase. Okay. So, the convective heat transfer is helped by adding insulation because of the additional area. Conduction heat transfer is going to be reduced by adding the insulation. So, these are two parallel mechanisms which compete with each other, and for a certain value of R, as we have seen previously, equal to K by H, the result is you get the maximum heat transfer. Okay. So, if you are below this value of K by H, increase the insulation thickness, increase the area available for convection, and that more than offsets the additional conduction resistance that you put in the system. That is what the concept of critical insulation thickness is. So, let us just work out with those, since R is equal to K by H, what are the typical values of K by H, and that would tell us something about when do you expect this concept of critical insulation thickness to be when you are going to encounter such concepts. So, let us write what are the typical values of K and the typical values of H, and then we will know what this is. So, K is for an insulating K for insulation material is roughly about 0.03 watt per meter Kelvin, and the H, the convection over here is mostly going to be the convection in air, which has the order of 10 watt per meter square per Kelvin. So, R C, the critical thickness of insulation, is going to be about 3 millimeters. Okay. So, this your size has to be less than 3 millimeter for the concept or for the occurrence of the phenomena associated with critical insulation thickness. Most of the normal conditions, you do not deal with 3 millimeter thin wire or 3 millimeter thin material. So, for most cases your R is going to be more than R C, and therefore, the concept of critical thickness of insulation is not relevant. So, concept of critical thickness, you do not encounter the phenomena associated with critical insulation thickness, since the length scale involved is only about 3 millimeters. So, what we see is that I increase insulation and I reduce heat transfer. But one example I can give you which would show the role critical thickness, insulation thickness may play for systems. So, when you think of very thin wires which conduct electricity, okay, they can be less, their diameter can be less than 3 millimeters. So, when the current passes, the heat is generated, the ohmic heat is the joule heat, due to joule heating some amount of heat is generated, and you want to dissipate that. Okay. But at the same time, you do not want a live wire without any electrical insulation put on it. So, what you do is on that thin wire you put a layer of insulation, but what you get is something very interesting. You not only make it safe for the wire to be safe, since you have put as an electrical insulation, this electrical insulation is going to act as a thermal insulation as well, because the heat that is generated is going to dissipate to the atmosphere by means of conduction through the electrical insulation and convection to the outside. Now, if your radius of the electricity carrying wire is less than 3 millimeter, then you are enhancing the heat loss from the system by putting an insulation, electrical insulation on top of it. So, you serve two purposes. You cover the electrical wire with an insulation, and by doing so you are increasing the heat transfer, and therefore, the wire itself now can be at a lower temperature, which will probably prolong its life and will be less hazardous. So, critical thickness of insulation are mostly relevant in very thin electrical wires where you put an insulation on top of it. But for most of the practical systems, since the dimension that we deal with are the dimensions are more than 3 millimeters, you do not get that in most of the applications. But concept wise, it is very interesting that it is difficult to it is counterintuitive when I say that by adding insulation I increase the flow of heat. So, that is something which in this class you have seen that it is a peculiar nature of the phenomena which is a direct result of change in the heat transfer area with radius. As you go outward, the area increases and therefore, the heat rate remains the same, but heat flux will change. So, this class we have seen what is a radial system, what are the resistances associated with radial systems, what is the peculiar phenomena of critical thickness of insulation, and in next class we will very quickly go through what is going to be the equivalent form for spherical systems and something which is known as the overall heat transfer coefficient. And then we will go into systems in which there is going to be generation of heat at steady state and what would be the form of temperature distribution for systems which are generating heat on their own. So, that would be the topic of the next class.